Good morning, team.
Hey, good morning.
Welcome to Wednesday. All right, I want to show you something quickly from yesterday. We had one little hanging concept that I was blowing, and I want to just show it to you out of interest. See how the technology treats us today. All right, I'm sharing a screen. Get going whenever it lets me get going. Let's see, maybe I'll show you that as well. Falcon. All right, come on, share screen. Yes, we got it. Again, I just show you this out of interest. We'll have plenty of time to review today, but I just want to show you a couple quick things. So remember yesterday, we were looking at that Falcon problem and kind of looking at the max speed, and that wasn't quite working right. So the problem is this. We had our velocity vector here, which is great. And we said, okay, well, to maximize that, we wanted to maximize the speed. And so I could not, and I actually changed this in the notes before I posted it yesterday. You can't take the derivative of this and set it equal to 0. You got to take the derivative of the speed. So notice I said, yeah, well, speed is Pythagorean theorem. So I took the Pythagorean theorem, and it's that you need to take the derivative of. So you're not taking the derivative of a vector, you're taking the derivative of the scalar version of that, which is the speed. So you get the square root involved, and of course the derivative is a little more complicated. So here's our square root, take the derivative of it, the 1/2 comes down front, the junk is still there, you subtract by 1, chain rule says multiply by the derivative of what's inside, which is rather complicated. So since that's a negative 1/2 power, that drops to the bottom, and there's still the 1/2 and the 144 and the 8 up there, which I multiplied the 1/2 through. And so now this is all equal to 0. Well, that's really good news because the square root just can get multiplied by both sides. And so then we're left to solve this equation right here. And that's kind of a wonderful equation because you can't solve it. I think that's really good for you guys to see at this stage of math. Since there's a sine of 4t and a 4t, those two worlds, the sort of linear and sine wave, you're not going to solve that. So if you go to Desmos, you get a whole bunch of answers to that, as you might expect, since it's a sine wave. And so these, and I'll show you this quickly on the other screen just for the fun of it, but these are the different, excuse me. Remember, zero slopes don't mean maximum, they mean maximum or minimum. So I took a kind of a quick look at the graph just to kind of resolve all of this, and basically every other one of these was a maximum. Every other one was a minimum. So I just want to show you really quick that kind of worked, and then also just leave you with a bit of at least a conceptual sense of why this is true. I'm going to shoot a picture of those so I can switch screens. So if I go over here to the So for instance, I'm just going to type one of those times, and I'm interested to see if you can kind of tell me what you think is true about this. So I'm picking, let's see, 1.528. 1.528 was one of the times. So if I go there, the question is, do you see that that's a very distinct location? Where am I on that flight path?
When the tangent's 0.
Yeah, notice it's like right at kind of the apex of the turn right there, if you will. So it turns out that's where all the slowest speeds are, which is really, and visually that's where the shortest vectors would be. So just take note of how long that vector is right there. If I push play now, see how it got longer? That time is kind of way too fast, but you see how it's actually at its shortest right there when it hits that apex? Do you notice it gets to its longest about right? See, it's getting longer, longer, longer. I mentioned this yesterday, but it's like boom, about right there. Well, that's where the maximums are, the maximum speeds. And you can sort of think of this like a car in the sense that, you know, when you take a corner, you might be sort of going your slowest around the corner, and then you get out and then you start speeding up and you reach your maximum speed at the inflection point, and then you say, okay, now it's time to kind of start slowing down so I can make that next corner. I mean, is that kind of cool that the math works out that way? So that was a minimum, just for the sake of it, because it's fun. If I go to the point, well, where the time is 7.305, this is a maximum. This is one of the maximums. 7. Actually, that might be too far to even see. Let's go 5.668. So that left the building because I was zoomed out too far. I'll back up to 2.424. That's the spot we just looked at a second ago. So that's the mathematically derived. That was a maximum. And we won't go down this road, but notice in the graph, we can actually look at the graph and tell, oh, that's a maximum because look how long the vector is. But remember, you can find out whether something is a maximum or a minimum by even one more derivative, like the second derivative test. If we took the derivative again, you may remember that whole business of being concave down and concave up. If the second derivative is positive, that means the slope is on the increase at that point. If the second derivative is negative, that means the slope is on the decrease at that point. So you could actually mathematically tell. So that's kind of cool to think about. Kind of cool to understand. I want to show you one other quick thing about 14.5. This concept of curvature. Just want to leave you with this concept because it's kind of cool. The thing that we, I guess you could say, didn't have time to do. So I want you to look at these vectors. And I want you to look at the kind of the bottom two. Let's see, maybe I'll turn this on and let it cruise while we look at it. See what kind of speed we're on. Yeah, nice and slow. I want you to see if you can tell what those vectors are doing. See that one, how it's kind of like pointing down and then it spins around and points up. Let's take it all the way back to the start. So do you see the one that's up is actually perpendicular to the other two? What are those two on the bottom? What do those look like they're doing? Let's push pause and go take a closer look. See if I can get this in a view where you can sort of see it good. Would you agree that sorry, I'm having trouble getting this thing to behave itself. There we go. Two of them, and I want you to think of it like this. You can see the one that's in the front. That's the typical vector that's our velocity. So it's kind of aiming in the direction of travel. But the other one that's off to its side is kind of cool because it's actually defining the plane in which you're in. In other words, I kind of mentioned this yesterday, but it's kind of like that vector V in the front that's kind of guiding the flight. Here's a pretty good view of it. So this vector is the one you already understand. So this is what 14.5 is about. This is the one you already understand. That's the direction you're traveling in. That's the velocity and so forth. But what this is really behaving like is, well, think of the path as being like an airplane. If this is the fuselage of the airplane, then that over there on the side is actually the wing. And so you probably have a sense that if you're, flying along, I guess I have to have T-Rex wings so you can see them. If I decide I want to turn, I got to kind of change my orientation like this. And ultimately that's called torsion. So, you don't just turn kind of this way when you're in an airplane, you kind of have to tilt up in order to make that turn. And so really that vector facing forward and the one facing the side, they kind of define the plane in which you're flying in right now. And ultimately the length of this last one on the top is kind of defining sort of the torsion or the, how much desire there is for you to turn a different direction. So basically, if you change the way this vector orients, then you're going to sort of change you're going to tilt and turn sideways when you're in your plane, if you will. And then this one that's vertical, does it make sense if I turn sideways? I could also kind of bank and go uphill or downhill. So in a sense, it takes these, one of the things that happen, the only reason I want to say this to you is not to kind of overwhelm you right before the test, but if you take physics later on, it's kind of cool to understand that you're used to this blue, red, green coordinate system as being a fixed coordinate system in space and time. But what happens even in my dynamics class in engineering is you actually have a coordinate system that moves. I mean, those three coordinates right there are actually all 90 degrees to each other. Well, not 90, but they're all kind of their own coordinate system, if you will. So when you're at a particular point, and that's kind of the way you think about it as an airplane. If I'm sitting here at the airplane at this point right now, well, then that's my direction of travel. There's my wing off to the side perpendicular. And then this vertical one is kind of my top, if you will. And you actually do your math entirely based on the coordinate system and the point that you just happen to be at. What's amazing about this is notice this is a pretty complex curve right here. That's a really confusing, crazy curve that this is flying along. And the amazing thing, and maybe you understand this from calculus, is that when you're at this point right here, does it make sense you're just someplace on a curve? Well, if you just look at a teeny chunk of that curve, does it make sense that could be thought of as just a circle? Circles are pretty easy to work with. So in physics and in applications of physics, that business of a coordinate system and curvature and so forth. So the only thing we're really missing, if you will, conceptually is, do you see how some of those corners are sharper than others? So that also might be a question you would understand. As I said yesterday and said a lot of times, the most beautiful way to look at math is just asking interesting questions. So you can appreciate if this is a car or an airplane, you would say, ooh, that's a really sharp corner down there. Well, there's a number you can assign to that. That's what curvature is a number that you assign to how sharp that corner is. Whereas this one up here, not near as sharp. So that's going to kind of have a smaller number. So being able to define that, being able to talk about the curvature of it, and it's based on the lengths of these vectors right here. So I don't want to belabor that point anymore, but it's just, I wanted to show you that at least just because it's kind of beautiful. It's kind of neat. And that's kind of what makes vectors so powerful. Anywho. So to the real business at hand today. So all I want to do with the rest of our time is just kind of make sure you have a really good sense of what's going to be on the test and that you just ace this thing on Thursday. As we did last time, I'm just going to open the test up at 8 o'clock in the morning tomorrow, and you can take it at your convenience tomorrow. I think I said 2.5 hours. I can't remember. We want you to have plenty of time, so you can work around your own schedule. This thing just does not like to share a screen. What is the deal? So I'm going to bring up the review. I hope you should be doing the same thing. Share the screen. Google Drive, where is that review? Right there it is. So let's just take a quick pass at, what is all this about? You will have, and I'll say this on the test too, but you can use GeoGebra for this. I want to see, notice I said verify your solutions. I don't want to see anything that's just straight from GeoGebra, but you're more than welcome to kind of verify and kind of play with it, make sure you're seeing what's going on. As you're looking at these questions, make sure that you're kind of looking at the note sheet that I gave you, because that's also going to be, something you have in front of you. So I'll put it in there with the test. You maybe already have it up and printed and so forth, because we've had quite a few pages. There's like 3 pages for this class, but I really just broke it down to just 1 page on there. It's just the last section, because we've covered a lot of stuff now. So can you still find the angle between a couple of vectors? You should think, okay, yeah, I can, but where's that formula? What's the trick to finding a vector? What's orthogonal mean? And again, you can, and it's part of the reason I just showed you that application, because here I'm just asking you a totally sterile question, which is find a vector orthogonal or perpendicular or normal. And by the way, that's what that's called. The one that was facing up a second ago is called the normal vector. Normal is another word for 90 degrees. So here, this is just an irrelevant question. Why would anybody care? Here's 2 vectors that have no purpose. There's no speeds, anything that's associated with them. Just find something perpendicular to them. But you can see that skill that we learned would have, paid off if we had a little bit more time to kind of play around with curvature and so forth. So can you do that? You should have I don't know, I hope this is still in your head, but dot product was ultimately the invention that allowed you to find the angle between a couple of vectors, and a cross product actually produced a perpendicular vector in a very efficient way. You don't have to have anything memorized for that. You can pull that up entirely. So, and then 3 through 6 is kind of an interesting question, because I give you 3 points that define kind of a triangle. And for those of you that are in linear algebra, this probably means something to you, but this kind of R3 thing there is really just saying 3D. So, and you could, obviously it is, because you have, an X, Y, and a Z. So it's not that I needed to tell you that. So could you find an equation of a plane through those 3 points? That's a good question. Can you find the angle? Do you remember what angle ABC means? It means B is at the vertex of that. So this is A, and this is B, and this is C. I'm certainly looking for that angle right there. So you got to be careful to, kind of pick the right one. And then could you find the area of that triangle? That's a rather interesting question. Could you find the intersection point of that plane that you found and this other random line? So again, it's good to work on your intuition. Intersection point of a plane and a line. Yeah, that makes sense. So if you had a plane and a line, if I had a plane and a line came down and hit it, that most likely is just going to pierce through the plane at one point. Does that make sense? it's not impossible that the line could be lying on the plane like this, which means it has all the points in common, but that would be unusual and kind of boring. And in this case, I said, find the intersection point. And so, I certainly made it up so it would do that. But again, doesn't it feel like it'd be kind of cool to graph the plane in GeoGebra and graph the line in GeoGebra, and then kind of look and see, graph the point you just found? Like you don't need me to grade this stuff. If you have a little extra time, you can leave me notes that say nailed it or something's wrong here. I don't know. So cool. And then you have two planes here, and I hope you have a pretty good sense that the 4x minus y plus 3z, the 4, -1, 3 was the normal vector or perpendicular vector, orthogonal vector. So planes were defined by that normal or perpendicular vector. So you see, so the 4, -1, and 3 determine the orientation of the vector. The 2 actually just kind of slides it around, of the plane. So you found the angle between a couple of vectors. Could you find the angle between those planes? That was kind of a surprisingly complex approach. And we looked at the time, the easiest way to do that was we recognized that the two planes would have an angle between them, but that would, since their perpendicular vectors are perpendicular to both of them, that the angle between the two perpendicular vectors would be exactly the same as the angle between the planes. And so that was kind of a neat way to do this. And then, of course, if two planes run into each other, of course, it's possible they're parallel. But if they run into each other in some fashion, then they would intersect in a line. And so could you find the equation of that line, find the line of intersection of those planes? And then I think this is kind of a cool question. Consider the position of a leaf in the wind. That's a good example of kind of a weird path that something might take that's natural, if you will. And of course, I obviously just made that up. It's not something that's realistic, but it's got, a parabola and then a sine wave for the y, and then 4t for z. So that's kind of cool. And it's going to fly for 6 minutes. That's a really, really tall tree, apparently. So now that I kind of have that position, that vector valued function, or that parametric version of its equation totally dependent on time, then there's all these cool questions that we were just talking about. Like, can I know its velocity? Can I know its speed? Can I find the equation of the tangent line to the path? Seagull. What the heck is a seagull doing in here?
I was wondering where that came from.
Oh, that's hilarious. I must have decided after I made the graph that a leaf could never do that or something. I don't know. Leaves can't go back up in the air. I'll make it a seagull. Oh, that's hilarious. So you should see that as, related to the velocity. In other words, the velocity pointed in that direction, the velocity vector pointed in that direction, but could you actually find an equation for an entire line? And of course, that line would change, right? So notice I gave you a particular time at 2 minutes. So that line would be pointing different directions at different times. And then, of course, could you find the acceleration of the leaf? Is it speeding up or is it slowing down? We're back to a leaf again. It was a seagull for just a second there, and then it went. That happens in calculus. In calculus, for an instant in time, a leaf can become a seagull. And then, again, kind of a cool question, similar to the golf ball problem, where you're ultimately trying to come up with the equation yourself. I would say, in the interest of time, if you want to be, that you really, those questions are awesome, but don't do them as far as reviewing for the test. Just do them if you think they're kind of cool. And there's another mistake because it says question 13 through 15, but 16 is part of that too. I've been having a bad day when I made this.
Oh, there's not going to be any problems on the test like that?
Yeah, so I'm not going to give you one of those. It's too time consuming. It would take the entire test, and it's also, on the hard side. I think you got plenty to think about just in these first 12 questions. So we'll keep it a little simpler.
Cool.
I feel like I understand that more than I understand the rest of it.
You'd rather have. Okay,
Uh-oh.
Connor wants that
Yeah.
other question. So
Well,
sorry, everybody.
I'll take your word for it. I'm just saying, like right now, like I feel
Yeah.
more confident in that.
Yeah, I understand that. So really what I would like you to do is, just given the time we have in class right now, is just pick the ones that you think, I'm not so hot at that. Like just take off in all different directions and just ask me questions. I think I've already posted all the answers to this, so you can just pull the answer up and kind of check. And maybe you don't ask a question because you got it right, or maybe you look at what I did and realize what you got wrong. But obviously, I just want you to sort of feel good about all these. And then, of course, you're more than welcome to say, would you just do number 9 or whatever for us?
Maybe 3 through 6.
Yeah.
Yeah, those are kind of ugly. Let me go find my pen that flew across the floor. Okay, yeah, let's do those. So I'm gonna share the screen. So I just need a piece of paper. Kind of don't want to change that leaf back to a seagull. That's kind of fun. I like that. I should just leave that there.
It'll be like a classic word problem where it starts out as Bob buys 300 watermelons and Jane has 200 bicycles. What is the height of the roof that Ken is standing on?
That's exactly right. So the penguin said, I'm not your radio. Okay, so we got these 3 points in space, and the main thing, like for the first one, you're trying to find the equation for the plane. The main thing you need to see, actually, I'll ask you guys this. What do you need to know really badly if you want to find the equation of a plane?
The perpendicular vector.
Exactly. You got to find that perpendicular or normal vector. And so there's more than one way to do this, but when you see that word perpendicular, you should be thinking cross product. That's what produces a perpendicular vector. That's kind of our little tool that we built, if you will. And you probably don't feel great about that. You probably, I mean, we kind of looked at it at the time and I helped you understand what that was accomplishing. But you probably don't feel great about that. We looked at it once and now it's been 3 weeks. And so, I don't understand how that tool works. At this point, I would say, well, let's just use it. Cross products produce perpendicular vectors. Well, the problem is to make a cross product, I need 2 vectors. It takes 2 vectors to do this. And so now we're actually getting somewhere. So then I say, okay, well, how am I going to get 2 vectors? Well, I got to go make them. So since, let's see, I guess I'll do it this way. Since those are my values for A, B, and C, then how do I know kind of which vectors to choose? Or how do I know which points to choose? Like, do you see what I'm getting at? What?
It's
Okay.
2 vectors in the plane that you want to be orthogonal to.
Yeah,
Take a cross
And
product
notice-
of them.
that's exactly right. And notice I have, 3 points in which to do that. So for instance, I could say, well, I guess I don't care. I want to go find vector A, B from A to B. So it starts at A and goes toward B. Well, you may remember that that is found by taking B and then subtracting A from it. So let's see, if I go -1, I'm also thinking I'm subtracting backwards, but -1 minus 2 would be -3. 4 minus -6 would be 10. -2 minus 4 would be -6. Correct me if I do something stupid here. So does it make sense that, you know, with these 3 points, if I just kind of draw them randomly in 2 dimensions, so A is not at 0, 0, 0. A is somewhere out in space. And so by subtracting those, does it make sense I have this vector right there now? And then I need another one. And actually it doesn't matter where it goes, although I think it'll look nicer to us if we kind of did that, like if we found vector AC next. Because when I take the cross product, then I'm going to get this kind of third vector up here in space that's perpendicular to both of those. How's your 3D view? Can you kind of see that a little bit? So that's what I need. So I need AC. Well, that's no different. I'm going to have to take C and then subtract A from it. So C minus A. So 3 minus 2 is 1. 5 minus -6 is 11. 6 minus 4 is 2. And so now I have, as Vale said, 2 vectors that are actually in the plane of the triangle. They could be anywhere in the plane of that triangle. It's just the only points I know are these. And so there's other vectors I could find. Notice I went from A to B, but I could go from B to A. And I went from A to C, but I could go from C to A. I could also do B, C. I could go from B to C or from C to B. There's actually 6 vectors that you could make. Easy ones anyway. You could even make it worse and like find the midpoint of this and then go over there. Like any vector that you want will work. So I'm just, you know, do the easy ones. So now I'm going to take their cross product and be looking at your note sheet with this so that you feel like you have something to fall back on. So what's a cross product? Cross product is where you say, all right, I'm going to keep track of X and Y and Z. And it doesn't matter what order I put these in, -3, 10, -6, there's my AB vector, and then 1, 11, 2. And now we're going to take the determinant. I mean, this is a crazy cool tool. Remember, it's just a mnemonic device. So one at a time, I say, all right, I'm going to cross this out. 10 times 2, which is 20.
I had a quick
Minus,
question about that.
please.
So do you want us to find the determinant that exact way? Because I know other ways to do it that I use that is easier for me.
Absolutely. No, I don't care.
Okay, cool. I
Write
didn't know
that
if you were
down.
going to test us on that exact
No.
method.
Cool. Write that down and get the answer. I consider that to be just math. I mean, I would say even to the point where, you know, if you could just type this into some kind of a cheat system. I'm sure there's software where you can just type that in and maybe that's what you're referring to.
No, I like to take the first 2 columns and then put them on the right side. It's another, it's still, there's still a lot of work that I could show for it.
Yeah, I don't care as long as you get the answer to this right and at least show me something because it is really easy to make a dumb mistake here, like in signs and so forth. So go slowly, like maybe even do what I'm about to do, which is to say, okay, 10 times 2 is 20 minus 11 times -6 is -66. Oh, that's actually 20 plus 66. So that's 86. And I'm remembering that's my X component. I mean, so you could just write it this way. You don't have to have, you know, IJK, or you could write 86I and then move on to J. Okay, cool. So that's good. Then I go in and say, okay, now this is gone. So then it's -3. I'm sorry, -6, and then minus -6. So that's actually -6 plus 6. Oh, that's interesting. That's actually 0. So that's 0J, and I got lucky because that was 0. But if I'd gotten like 7, what do you got to do to that number? According to your note sheet, what's unique about the J term?
Subtract it.
Yeah, it's the opposite sign. So if I got 7, then I got to write -7. If I got -9, I got to write +9. So I got lucky since it was 0. So this is a bad example. Like I really wouldn't want this to be a problem on a test. I made it up randomly and that's kind of what happened. And then the last one would be this. So I've got negative 33 minus, it's always minus, and then positive 10. So negative 33 minus 10 is negative 43. So that would be minus 43K, or I just put minus 43 down here. And so what I have then is I now have my normal vector. Which is cool because that means I now know that this is my equation. I'll go ahead and write the y term in here, even though you really wouldn't need to. In other words, I know I know the majority now of that equation for that plane, because the normal vector is coefficients for x, y, and z. How am I going to get what it's equal to? So what this tells me is I have the orientation right, but I might not have the kind of the height right. I hope this is easy and does not require memorization to you. What do I do now to get that last part that I don't know?
Can you just pick one of the points on your ABC?
Yes. Pick one of the points. So I'm going to pick A, 2, negative 6, 4. So 2, negative 6, 4. So what do I get when I plug all of that in? That's all I got to figure out. So 86 times 2 minus 43 times 4. I got 0. That is just weird. Can't believe I actually made a problem up that did this. So, bam. Now, of course, if I had time, I would want to stick that in Desmos. And if I was you, I would probably not do that first. I would just say, sweet, I got the answer. Maybe I wouldn't box it or whatever. I just kind of move on to the next thing. In this particular problem, I go on to ask other things that might require, because I could have made a mistake here, right? Like a dumb mistake. Maybe this isn't the right normal vector or something. So in the event that I was going to go on and use it for other questions, I probably would check it right now, even if I was a little worried about time. So of course I'd graph the 3 ordered pairs. Remember that's in GeoGebra, that's capital A, capital B, capital C, or whatever. And then of course I'd stick my equation of my plane in there, and I'd be, folding my hands, praying that the plane would actually go through those 3 points. If it did, whew, sigh of relief. I don't have to go check all that work, see what stupid thing I did.
So
Feel good about that?
I don't know if I'm in, my open math land, but I have been doing 86 times x to the minus 2 plus, that would be y plus 6 plus negative 43. And then, so it would come up with something on the right side. Is that still correct, or?
Yeah, there's another way to do this that's even more memorization. If you looked in the book, there's a trick here where you can say, okay, yeah, what you said. It's kind of like, because one of our points is 2, if you just pick, then you can say x minus 2, and minus 43, and since z is 4, then you can just type z minus 4, and when you do all this, you can just put 0 on the other side. And so that's kind of cool, but it's just one more thing. That's kind of why I didn't show it to you that way.
It's fine. I mean, as long as I don't get it wrong on the test, I just
no,
didn't
you
know if
won't.
it made a difference.
No. I don't know if you guys looked in the book on that, but that's kind of neat. In other words, it will be equal to 0 if you do that. That's kind of the idea. Because what that does is shifts it, right? In other words, if you say instead of x, if you say x minus 2, then you've said, oh, I'll just shift it right 2. Well, if you're doing that to get it to go, if it goes through this point, you're effectively shifting that point so that it goes to 0, 0, 0. Since next needs to be 2, then if I go x minus 2, then I would shift it right 2, which will actually make it go to x is 0. And so that way I can just stick a 0 at the end. And so that's faster actually. So yeah, no problem with that. Great. So then what about the angle ABC? Notice I get kind of unlucky here, because if I want angle ABC, then It's this angle that I want. So what would have been lucky is if I asked for angle BAC, because we already made 2 orange vectors up there that have that angle. In other words, those 2 vectors I just had, I'd be able to use those and not have to do this over again. But that's okay for us because we need to think about this anyway. So if I want, and I'll just redraw this down here for question 4. And I'll redraw this in a completely different orientation. So I'll just call this ABC. So if I want angle B, then I really need that vector and I need that vector. This is important this time that they're going that direction. So this one, of course, would be called vector BA since it goes from B to A. And this one would be from B to C. And so I'm going to need those 2 vectors. So BA, copy. How do I do that? I guess I'll just drag it down here. So if I go not B minus A now, but A minus B, 2 minus -1 is 3. And -6 minus 4 is -10. And 4 minus a -2 is 6. And so that should be the same exact vector I got for AB, except all the signs should be backwards. If I was memorizing this, I could have just looked up at this one and said, oh, I'll just rewrite it, except for change all the signs. And then B to C, I got to go C minus B. Is that the one we already did? No, it's most certainly not. So C minus B, 3 minus -1 is 4. And 5 minus 4 is 1. And 6 minus a -2 is 8. So now I have those 2 vectors. What do you do to find the angle between a couple of vectors? What's my approach? Yeah, that's dot product. So we say the cosine of the angle that we're supposed to find is equal to the dot product of those 2 vectors. So dot product is x times x, 4 times 3 is 12, plus 1 times 10, plus 8 times 6. So there's the answer to the top. And then on the bottom, I need the magnitude of those vectors. And I'm multiplying them by each other. So I can do this in my head, 16 and 1 and 64. So that's 81. The square root of 81 is actually 9. Oh, that's amazing. We got lucky there. Is that right? Is it really 81? It is. So that magnitude then, at least this first one, is 9. We'll get lucky on the other one too. Second one would be 9 plus 100 plus 36. That's 145. So we get the square root of 145. The only thing important here would just be to, give the answer appropriately. Like you're going to find an angle. I think the thing you'd want to do, just because you are going to maybe look at the graph and kind of make sure that it looks right in GeoGebra, you'd probably want to do this in degrees, but at least label it. So I'm going to do it in degrees. I'm in degrees. Good. Second cosine of, let's see, what's that number on the top? 50. 50 divided by 9 divided by the square root of 1, 45. My machine says that would be 62.5 degrees. Don't care how you round it. So again, I'm going to go straight over to GeoGebra and kind of look and see. I know what 60 degrees looks like, so that look reasonably close. I'll spin it around. Ah, sweet, that looks good. May even be some way to cheat in GeoGebra. I haven't looked into it and ask it, like, what's that angle? Maybe it somehow could tell me that. That'd be kind of fun. You may remember, just out of interest, that Raymond looked into, because I asked you guys, what's the genesis or the history on the dot and the cross product, and what he uncovered was, I'll do a terrible job drawing this, but I forgot who the mathematician was, but somebody was studying a tetrahedron, which is really just a four-faced equilateral triangle figure. And part of studying that is to figure out, what angles are going on there. Well, notice how cool it is. Like, see how you could do that now? I mean, there's 3 points for a triangle, just add a fourth point. And so we can find angles between these things now. That's just really cool to think you can understand that. So ultimately he invented it as a tool, because not because he was, enjoying math necessarily, although he may have been, but because he had something he wanted to do. It's like, hey, there's this cool shape. Turns out there's 4 platonic solids, which means a solid that is made by equilateral shapes. A cube is one of them. 6 squares, perfect equilateral 4-sided figure. 6 of those makes a 3-dimensional shape. 4 equilateral triangles makes a tetrahedron. So he's studying that for whatever reason. So now we can find the angle between them. That's awesome.
Fun stuff.
Yeah, it's so cool. Let's see, I'm trying to decide if I'm going to do area of a triangle. Let's do it. The only reason I'm questioning whether to do this is because I don't think I taught you this using kind of the tools. I think we played around with this entirely based on, maybe I'll just talk about the logic of it. One of the reasons I don't think I'm going to do this is I'm not sure I'm going to assign it, like as a test question. But you should know from earlier study in math that if I knew this length right here was, say, 12, that the area of a triangle is base times height. And so the height is not one of the sides. So if that was 12 and this was 10, then I go 1/2 times base times height. And so I get 60. And so, but let's talk about this just at least a little bit. Do you understand how to find this length right here? If you knew ordered pairs, what would you do to do that based on what we've learned?
Just find the magnitude of that vector AB.
Exactly. Like we had the vector AB earlier. Can't you just find the magnitude of it? It's Pythagorean theorem. But the key is it is the vector. It's like you got to subtract the x coordinates to get the x of that vector. So that's not terribly hard to find. And then perhaps I could employ, if I wanted to kind of use a more tool type of approach, I could employ a cross product maybe to find this vector, because ultimately that's kind of what I'd like to find, is that vector right there. Maybe I'd find it as a vector. The other thing you could do is just find it a little bit more manually. Remember that if you take the dot product of 2 vectors, and you get 0, think about what that means up here. If you took the dot product and this was 0, notice now you have the cosine of theta equals 0. Where are you on the unit circle when the cosine is 0?
Pi over 2.
Yeah, you're at 90 degrees, or pi over 2. So if the dot product is 0, that means those 2 vectors are perpendicular. Well, hey, that's what I need right here. I need a perpendicular vector. So there is kind of a sterile way to do this, but I'm just saying, if you're playing around with this question, you could say, well, I need a vector that's perpendicular to this, and I need it to go through this point C over here. So the cool thing is you could literally invent one. Like you could actually find the equation, not of that vector, but of this entire line. And then just make sure the line goes through point C up there. And then now that you have that line, you can see where these run into each other and then do the distance formula again or the magnitude again. But anyway, there's kind of a lot to that question if you don't, and I don't think I have on the note sheet anything that's any kind of a memorized technique for that. Just looking really quick. Oh yeah, I do. I did put this in the notes. This is the memorized technique for that. So I was kind of looking at it a little bit more logically. But I don't think I talked to you guys about this. I put this in here, but I don't think I talked to you guys about it. So anyway, I don't think I'll put that on the test. And I would like to talk about the last question in that, though, number 6, because I think that's kind of a neat question. So find the intersection of a point, intersection point of the plane and this line. So would you agree that I could write this line? So it's written in, I don't even know what form that's called, but really I could write it in what looks more parametric. It's kind of like defining. Notice I'm not even writing this with vectors. I'm writing it as just an ordered pair. Like here's how you find your ordered pair. You take 2 minus 4t, that's your x coordinate. 6 plus 1t, that's your y coordinate. And then it's -8 minus 2t. So the question is, when does that run into our vector or plane that we got a little while ago? 86x plus no y minus 43z equals 0.
Wait, I'm confused by that because that would be, wait a minute. Oh, okay, maybe I get it. So the 4, 1, -2, which vector was that? Where did you get that from?
I'm looking on because that's question 6 is saying find the intersection point of the plane that we found earlier and then this new line that was part of question 6. So the new line was
Okay.
started at the point 2, 6, -8.
Oh, I see. We're moving on to question 6 now. Sorry.
Yeah, this is question 6.
Question 5 still.
Speak up. Good for you. Everybody should do that. So I want to see where these hit each other. So what are your thoughts? How am I gonna do that? How could I find where these, again, I'd prefer you reason it out for yourself more than anything else. By the way, just as a side note, is it okay to do this? Turns out 43 and 86 have something in common. The answer is, yeah, it's the same exact graph. Maybe that'll make my life easier. So how am I going to do this? How do I, is your first thought kind of like, huh? You know, how do these, I mean, the bottom one has X's and Z's. In this case, just happened not to have a Y, but, and the other one has a bunch of T's. It's like those aren't going to talk to each other very good. What's my approach? Well, isn't this X? And this is Y and this is Z. So down here, then couldn't I say 2 times not X, but 2 minus 4t, since that's what X is, and minus Z would have to equal 0. By putting those two together, notice I get an equation that only has one unknown in it. So I'm actually going to be able to find the time. if you will. It's not really time in this case, but I'm going to find this value for t that works here. So I end up with 4 minus 8, t minus a minus 8 is plus 8, minus a negative 2 is plus 2. So I end up with negative 6t, which if I add to the other side becomes 6t, and then I have 4 and 8. Oh, look at that. That's probably why that one came out so nice, because I was trying to make whole numbers out of this. So instead of t being some weird number, exactly 2. That's really nice. But the question was, find the intersection point. So does it make sense then that I would say, oh, well, if I know what happens at t is 2, then I could throw that 2 back in every place it goes. And I would literally have an ordered pair then, or an ordered triple, I guess you would call it. And then again, of course, I could go to the GeoGebra and kind of see, wow, does that line really run into the plane and the point that I think I just found? That's kind of cool. What else shall we look at together?
On the homework, we had a question that talked about finding a plane that intersects a line and a point. Are we gonna have anything like that on the test?
If it's possible to be on the test, I'm going to have it here in this review.
Okay, because it looks like you have find a line of intersection of the planes. Yeah, it doesn't look like you have it on, so that's good.
Was that hard? Did you get
It
it
was
right?
an absolute nightmare for me. I like followed the video step by step after a while, and I still couldn't get it right. I didn't.
Yeah, I think I had the same thing where I literally just copied what the video was doing step by step with my own numbers, and I still got the wrong answer.
Yeah, it was terrible.
So it was a plane through a point and a line.
Yeah, so it was a line, and it wanted the plane to like pretty much dissect the line like along the entirety of it, and then it gave you a point in space, and it wanted it to intersect that as well. So it looked kind of cool, but I just couldn't get it to work.
Yeah, and for me personally, I always, like we were taking the cross product a minute ago to get a perpendicular vector. I struggle with stuff like that conceptually, because again, you tend to, if you will, watch somebody do it. And it's this is a good place to have videos connected to assignment questions, I think. But if I just watch somebody do it and they say, well, yeah, cross product will produce this, and I just kind of say, oh, well, okay. Then I do it, and maybe I get the problem right. But that bothers me when I think I don't understand conceptually why that works, or why does a cross product do that, and so forth. And yeah, I remember looking at that question too and thinking it's kind of convoluted. I won't go into that here, but just as a point of consideration, anytime the question says, hey, you need to find the equation of a plane, again, your first thought should be, okay, that means I need a perpendicular. I need some perpendicular to it. So, my thought here, just logically then, would be, oh, okay, if that's true, then I'll pick some point on this line, and I'll pick another point on this line. And you could do that easily. Isn't that simple? Like, pick t to be anything you want. I can find 2 points. Well, now I just do what I did before, which is, hey, there's a vector and there's a vector. And now I can take the cross product, and I found a perpendicular. I found the perpendicular that I was after just by finding 2 points that are on that line. I'm not sure if I watched it.
Would you take the perpendicular and form an equation with the point then at that point?
Yeah. So at this point, this is exactly like the triangle is my point. Like the original problem, we had 3 points, right? And we found the equation of the plane through the 3 points. Well, couldn't you do that here? Just find your own points. There's 2 points that are on that line somewhere. If the equation was, something like 2, 3, 4 plus t times 3, 6, 9 or something like that, can't you just say, oh, no, let t be 1? Okay, well, 2 plus 3 is 5. 3 plus 6 is 9, and 4 plus 9 is 13. So look, I just found a point on the line. There it is. 1t is 1. What's the easiest one? T is 0. Okay, well then this is 2, 3, 4. Great. So, and then this point out here was given, whatever it was. It's like, great, now I got 3 points. So I can do that manually. I don't need anything else. So as soon as I have those two vectors, then I'll take the cross product, and that'll give me the perpendicular, which is the coefficients of the x, y, z for the plane, and I'm home free then. Maybe he used some more complex technique for that, but
Yeah, ultimately, I think I'm kind of with you where I don't understand. It was hard for me to understand what taking the normalized vector of something was at a certain point. And so I kind of made like flashcards of if I want the angle between vectors, I have to dot product. I have to like memorize kind of how the steps on how to do that.
yeah.
It's hard to like ration it for myself.
Yeah. And you should know this, it's taken me more than once to kind of make sense of this deeply enough. I mean, I spent a bunch of time showing you guys where the cross product came from. I won't reiterate all of that, but that took me a long time to kind of go, oh, that's what that's accomplishing. Because really conceptually, if this is a bar right here and they came over here and pushed on it with a force, then we figured out what the torque was, and the torque is really defined as kind of if you pushed around it, that being 90 degrees right there, then this is going to cause that to kind of rotate around that point. If I push on this right here, then it's going to rotate in that direction. And it's kind of like this is the axis around which it rotates right here. And so the answer that you're actually getting for torque turns out to be a vector that's perpendicular to those other two vectors. And so that tool was designed to calculate torque, which is a very practical engineering concept. But as a byproduct, what it's doing is producing a perpendicular vector. So we're just using it as a tool that tells us what a perpendicular vector is, but we don't really even care what size it is or anything about torque. And so it took me a long time to kind of, oh, okay, that's what that's really doing. So pretty tough to conceptualize that in one pass. I think your approach to, make flashcards and just think, what are these tools doing? Dot product is to find the angle, cross product finds perpendicular. To be able to kind of memorize that and see those as tools that accomplish those things is kind of where you want to be for your first pass at this.
Well, yeah, and Calc 1 actually goes over, or sorry, not Calc 1, Physics 1 actually goes over torque. And so it was something I wrestled with already and then ended up later on kind of understanding it a little bit more. And so it's hard to toss what I thought I had an idea of torque was just to find a vector essentially.
Yeah. Well, and that's because in physics, you're probably mostly taking two-dimensional. And so
it was,
in the engineering book that I teach, there's the scalar approach, which I like to say is the common sense approach, which I'm always in favor of because I want to see it in action. And then there's kind of this cool mnemonic tool that just kind of produces the answer. And that's a conversation we have when I teach statics and dynamics all the time because of the temperament of the people taking the class. Some people kind of like the memorized tool that just kind of gets the job done and takes care of all the signs. And, because sometimes one force is pushing one way, trying to get it to rotate one way, and one's pushing it the other way. And, my approach is I have to keep track of that mentally and say, oh, those are working against each other. So one is positive and one is negative. Whereas the mnemonic devices just pop the right answer out. So they both have their advantages. And the problem is in a book, you're not really going to be taught to think like that. You're not going to be taught it in such a way that you think I can understand it. You're taught it exactly like that video you watched where you think, I don't have any idea what's going on, but I'll just copy those steps and, get the heck out of here, which is ultimately not good.
Yeah, and ultimately didn't work.
Well, there's a lot of mistakes you can make. So let's see what else.
Could we go over number 8?
Sure. Find the line of intersection of a couple of planes. And so let's draw a quick picture. Boom, boom, boom. Yeah, there's a couple planes intersecting each other. And so we're after this line, right? Find the line of intersection of a couple of planes. How am I going to do that, you say? Let me draw this slightly different. I'm going to draw them 2 different colors. I'm going to draw this at kind of a wonky angle this time. So how am I going to find that? Well, what do you need for a line? Again, I love to, even though I hate cooking, I love to think of this stuff as recipes. It's like, go whip up a recipe of line. What are the ingredients? What do I need for a line?
Need a slope.
Yeah, I need a slope. In 3D, that's characterized by a vector. In other words, I'm going to need a vector which contains the concept of slope. And in order to get a vector, I'm going to have to have a couple of points. So, I need something where these two things kind of cross into each other. So, one option would be like, is there some way, a minute ago, we found a line that kind of pierced through a couple of planes. And so is there some way to just find a couple of points, like manually? I'll just find 2 points on that line, and then those 2 points will allow me to find my slope and my vector. Maybe that's possible. Maybe there's some kind of cool, mnemonic trick that would allow me to figure that out. But the easiest way, the thing that will stick with you, is just to try to find a couple of points. So let's kind of stare at those 2 equations for a second. So 4x minus y plus 3z equals 2, and 2x plus 3y minus 5z equals 8. So how do I find some point? Well, remember, there's a billion of them. That's what's kind of so cool about this. And so you can actually find those points, find a point like this, because notice the problem here is what we've got is 2 equations, but 3 unknowns. And if you've taken linear algebra, then you have a little bit more of a feel for this. But your first reaction to that should be, bummer, man. I could have solved it if it was 2 equations, 2 unknowns, or 3 equations, 3 unknowns. I could have solved it. But remember, if it was 2 equations, 2 unknowns, there'd only be 1 answer, which means there'd only be 1 point where those intersect. There's not 1 point. There's a ton of them. So of course there is. So one approach is to find a couple of points. Well, the cool thing is you can, I don't know, there's all kinds of things you can do. Like to find 1 point, I could say, well, I'll just pick, and by the way, this isn't the easiest way to do this, but I'm going to say, I don't know, I'm just going to say x is 3. So, that line goes forever, right? The red line actually goes forever left and right. So isn't there some point on it where x is 3? Now, easier would be to pick x is 0, right? But just to show you that you can think, if x is 3, then see what happens to this. It becomes 12 minus y plus 3z equals 2, and 6 plus 3y minus 5z equals 8. And now it's 2 equations, 2 unknowns. In other words, if you pick x to be 3, then there is only 1 point now. There's a very specific y and z that go with that 3 now that you've chosen that. So that's the cool thing about this. So then I say, okay, cool. How am I going to get that? Well, I probably should add 12 to the other side or whatever, but I'm not going to. I'm just going to say, well, if I took this one times 3 and added these 2 together, do you see how the y's are going to go away? So I have 36 and 6, which is 42. I have negative 3y and 3y, which is gone, mission accomplished. And then I have 9z minus 5z, which is 4z. And on the other side, I've got 6 and 8, which is 14. So that means 4z has got to be negative, what is that, 28? Oh, I got lucky. I got a whole number. So divide by 4, I get z is equal to -7. If I haven't screwed up, and maybe I likely have. So z is 7. All right, cool. Then I go back to, one of these equations. I'm just going to look at the bottom one. Let's see, if I take 6 over there, that'd be 2. So I have 3 times y minus 5 times z, which we now know is -7, and that would be equal to 2. So that's 3y equals 35, but if I subtract 35 over, that'd be -33, and I got lucky again, and y equals -11. And by the way, I didn't get lucky. I spent a whole bunch of time making sure this problem came out nice, because I wanted this to be a little bit easier for you. So I just found a point. So I guess we'll call it point A. Let's see, I picked x to be 3. I found out y was -11 and z was -7. So I found a point. So does it make sense? That's one of the ingredients. All I need is a point and a vector, and I can find a vector by finding one more point. So does it make sense to you that you can pick anything you want? Y is 19, z is 12. Z is 0. Of course, the smart thing is to pick something to be 0, right? Then you just don't have to work so hard. So let's not work so hard this time. By the way, I mean, should you change letters? Should I move to Z and say Z is 0 or Y is 0 or something? Doesn't matter. So I am going to change just to, again, be a little creative in the process. So I don't know. Who cares? Let's set y equals 0. Okay, if y is 0, then I'd have 4x plus 3z equals 2. And I'd have 2x minus 5z equals 8. And I'm lazy, so the easiest is if I just multiply this one by -2 and add them, then the 4x and -4x would be gone. And then I'd have 3z and 10z, which would be 13z. And I'd have 2 and -16, which would be -14. Looks like our luck just ran out. And when I say luck, it's kind of like bad luck that I picked y to be 0. I mean, I could pick y to be 1, 2, 3, I mean, all kinds of numbers. But it looks like for the particular y value that I just chose, I got a really ugly z. And again, I'm doing a lot of math. It's not easy, it's not hard math, but the chances of me doing something dumb are pretty high. I don't see anything though. So now I'll just go throw z back into this mess right here. So I'll take 2 then and subtract 3 times 14/3, -14/3. Thirteenths, I mean, 14/13. 2 plus 3 times 14/13. Answer, then divide by 4. I get some crazy decimal, cheat, have the calculator tell me what that fraction is. That gives me an x value of 17/13. So I now have my second point. I'll call it B, where x is 17/13, y is 0. So to me, this is the most logical approach to this. I'm doing this sort of based off common sense. I'm looking at my note sheet right now, and I did this a little more. I did this in kind of a different way. I did this using more of the mnemonic device approach, kind of things I taught you in class. But this is kind of cool that you can just do this manually. So is this the right answer then? If I say, cool, here's my line. It starts at 3, -11, -7, and it goes through this. Is this true? Not true.
No, because we have to have a vector and a line and a point. So
Yeah, this second needs to be a vector. The reason I wrote that out is because I think that's kind of a tempting thing to do, perhaps. But really, what you're doing is you're picking a point, fine, 3, -11, -7, but then you got to say what direction is it going? It's not going to that point. All you're doing is multiplying that point by different numbers. You got to have a direction. That's what a vector represents, is a direction. So I got to actually subtract these in order to get my vector. And again, because those are fractions, that's going to be ugly. And if you do look at my note sheet, you might notice the answer comes out nicer, and I'll show you how to do that here anyway. But I want to finish it. So let's see, what is vector A, B? So I'm going from A to B. So that means I got to go B minus A. So again, I'm cheating. I don't want to suffer. So I'm going to go 17 divided by 13 and then just say minus 3. I get some weird fraction. I get some weird decimal. I ask it for a fraction. I get negative 22 over 13. And then, oh, good, 0. 0 minus negative 11 is 11. So there I got one reprieve. And then negative 14/13 minus negative 7. So plus 7. Again, weird decimal. Convert that to a fraction for me. I get 77 over 13. So that is what I could replace this with. If I put this in here, then I'd have an answer that was good. Now, just a side note, something really cool that you can do here. I don't know if you understand this, but remember T, what's T represent in this? What is T? In order for this to work, what value does T take on? In order to create our line. Not a trick question. Should know the answer to this.
It's all the values, basically.
It's everything. In other words, to create all the billion points that make up a line, T's got to be everything. Well, notice this equation right here. Everything is divided by 13. So it's like, could I multiply everything in there by 13? So that this became negative 22. 13 times 11 is 143. And 77/13 times 13 is 77. Isn't that nicer? Perhaps you even noticed, though, that every one of these numbers up here was divisible by 11. So I could actually even go through and divide all of these by 11. That takes that back to, it's 11 again, and this would be 7. That's actually a nicer answer. Actually, that takes this back to 13, not 11. So isn't that a nicer looking answer? Doesn't matter though, I could have stopped with the crazy fractions and stuff that I had here. But you may notice if I look at my solution sheet, which I guess in the interest of time, I'll just quickly pull up. Because this represents the conundrum that I'm trying to kind of get across to you and learning these things. Calculus 253 solutions test, where are you? I just want you to see how differently I did it using the mnemonic technique on here. And yet we got the same answer. Well, kind of the same answer. So I said, find a point on the line of intersection. And notice I found a different point. I picked Z to be 0, and that was a really lucky choice because it gave me X and Y to be positive numbers. And so remember, there's a million points that are on that line. And so the ones I just found were different ones, but that was a particularly nice one. But then, wait a second, what did I do next here? The direction of the line of intersection is perpendicular to the normal vectors of the planes. So the second thing I would need is this vector, right? Which we just found by finding a second point. But here's a cool trick. The direction of that is perpendicular to the normal vectors of the planes. Again, I'm not sure how well you can see that, but I'll draw a picture quickly in a second. It's perpendicular to those. So that means if I actually took the cross product of those, that would produce the vector that's going the correct direction. Now, you're not looking at this, so you don't remember it, but a second ago I had a -2 here and a 13 here and a 7 here. Do you notice that that's just multiplied by 2? So if I looked at these and said, oh, look, they all divide by 2. So that's a 2, a 13, and a 7. That's exactly what I just had a second ago. So that's kind of a cool idea, isn't it? I mean, are we looking for a perpendicular? We're looking to something perpendicular. So that's kind of a neat technique. But again, that feels like a technique. I guess I drew a picture of it down here. This is kind of good to see it. So the idea is I have this plane here, and isn't that perpendicular vector right there? Like, because I know the equation of the plane, don't I just know what that is? In other words, the original, I guess it isn't written here, but the original equation was 4x minus y plus 3z. So isn't that the actual coordinates of that perpendicular vector right there? And then the same for the other one, 2, 3, -5. So here's the 2, 3, -5 one. And so isn't this direction over here perpendicular to those? Isn't that a cool idea? The fact that, isn't that a neat trick, if you will? But I think you can appreciate, if I was, watching somebody do this on a video, I might just copy what they said, but that's not going to persist very long with me. So that's, I don't know, kind of why I showed you what I just did. In other words, man, I wouldn't necessarily remember that little trick, but it's kind of cool that I can just get it manually myself. So this is the same as we just got a second ago, doing it a totally different way. But this original point's not the same. Does that bother you? Well, it shouldn't, because isn't there thousands of points here from which to start? The only important one is actually this direction vector over here. So I just found a nice point to start from. Well, we found a nice point too. 3, -11, -7 wasn't a bad point either. But again, cut yourself some slack. You guys are all good students to have made it this far in math. It's not easy to, get your mind around all of this in a way that you can, take it with you. This is the kind of stuff you have to address again later. If you go on in math or, applied physics or engineering or something, these topics will come up different times, and you will not just be expected to immediately remember them. But the question is, can you, get them back? Can you go look at your notes? Can you remind yourself by looking, watching a couple of videos? Can you kind of get it back? Very tough just to walk around. If you see me on the street 3 months from now and you say, hey, what's going on? And you ask me something about this, I probably won't just be able to pull it off right on the street. Like, I'd have to think, I don't know, let's sit down for a second and draw a couple pictures and, try to get it back. I mean, I've taught it, I've taken it and taught it, and I'd have to get it back. So, how much more you guys? So don't feel like you're doing something wrong if you feel like you're having to work hard at this. And, and you should also expect you're going to make some mistakes on this test. Hopefully they'll just be like math errors, that you watch me make all the time. Something not that important. Try to make your work nice and clear so that I can just, because I'll grade it, on my iPad, I'll circle it and go, dude, where you subtracted wrong. But, the question is, will I be able to see that? Will you have given me enough work that I can kind of tell where you went wrong? And of course, I'm just going to assign credit accordingly. If it's just a stupid math mistake, then I'm not going to take off very many points. So. All right, 9:24. I don't need to leave. So if you want to keep asking me to do another one, I have no problem doing that, but
Sweet. Thanks, Doug. See you next term. Looking forward to it.
Thank you. Can't wait.
All right. Sounds good. Bye.
See you, Doug.
Later.
Oh, Doug, by the way, I was going to ask you,
Yeah.
Is calculus graded on a curve? Is it 60% passing or is it 70% passing?
I don't grade on a curve unless I kind of look at the overall class. I mean, if there's people that are, if everybody was kind of way down there, which I never want to see that happen. There's a lot of kind of doctorate level professors that, the highest grade in the class is 52. I just think that's just a poor way to teach. If the best person in the class is getting 52, then you're asking too much. Like they don't have the prerequisites they should have. You're asking too much. It's like, and that's no fun for anybody. So I never like to see that. So I usually don't curve things because I try to teach and give enough reviews that you actually, there are people get A's on my tests. And so I don't usually curve things.
That's the thing is this term was kicking my ass, and I was talking to my buddy about it, and he's like, "Oh, well, those classes are graded on curves, right?" And I was like, "I don't think this one is. Like this one, I should be getting like A's on." So
yeah. So I look at that. I try to assign grades pretty. So I never put that on. I never put that in my syllabus, but I will kind of look at that and see what the top score is.
I don't expect to need the curve. I'm just curious. I looked on the syllabus form and I was like, oh, I can't find it. So.
Mm-hmm.
Thanks
Well,
again, Doug.
Yeah, good question.
Alrighty. So I'll see you next term.
Outstanding. Enjoy having you in class, Shane. I'm glad you're going on.
Yeah, me too.
All right. Bye-bye.
See you later. Thank you again. Have a good break.
Thanks. Bye-bye.